Okay, Mission 5, force diagrams. Remember you have the help section, and also remember look at the end of the video for a table of contents about the different missions. In terms of finding individual problems, you'll have to poke through if you're looking for specific kinds of problems. Okay, as usual, answer the question before you look at my answer. Well, maybe too late since I already put my answer down there. So a motorcycle is moving rightward, so it has to be a net force to the right. Air resistance is going to be in the opposite direction, so C should be the right diagram. The air resistance is bigger than the forward force, which is actually, think about it, the road pushing on the motorcycle, and then there's the F norm, the normal force, and the F grav, the gravitational force. And you can go through the others and see none of them match that pattern. So let's check. Okay, I don't need to keep reminding you when it goes to the next problem. You should just automatically pause the video and answer the question before you listen to my answer. So I'm just going to start giving you that prompt. That's up to you. And also look at the diagrams that are wrong and think about why they're wrong. All that will be helpful to your learning. So A is the only one that has equal and opposite normal force and gravitational force. So that should be the correct answer. Okay, pause. The squirrel is also A, right? Because it's going at a constant velocity, so the up force and the down force have to be the same. There's gravity, and instead of a normal force, this is an air resistance force. So the answer should be I, because there's, you say, well, D has a net force backwards, but there's no force pushing the sled forward, it's just gliding forward. Sliding to the left, so the net force has to be to the right, and there's only the force of friction. Nothing's pushing him forward, he's just sliding to a stop. So it should be D. So sliding to the right has to be a net force to the left. Whoops. And so it would be this one. And notice you can't, well, I don't think there's any here anyway, but all of them have, well, except for this one, all of them have the normal force and the gravitational force. Those are always balanced, but the friction force in this case is opposite the motion. Motionless from a bar, the up force and the down force are equal. Falling and speeding up, there's no sideways forces. The down force has to be bigger than the up force if the skydiver is speeding up. In this case, the up force has to be bigger than the down force. And think about it physically. Don't just say like in the world of diagrams. So how would that happen? The skydiver dives out, he's going very fast, opens the parachute starts to put more air resistance than the force of gravity and slows the skydiver down. So we want to stay thinking about real physical examples and understanding them as much as we can. So in this case, we still have the normal force and the gravitational force, but the pushing force, the applied force, and the friction force have to be equal and opposite because it's moving at a constant velocity. So it doesn't matter whether the skydiver's at rest or moving at a the trapeze artists are moving at a constant speed. The two up and down forces have to be equal, and there's no sideways forces. Okay, mass versus weight. Mass is measured in kilograms, and it's just that, mass, inertia. Weight is the force of gravity on an object. So weight is a force and it has units of newtons. So these questions will help you try to trick you into confusing the two. So answer this question and come back. Okay, here's the calculation. Notice this has nothing to do with it. The mass is just determined by the weight. And so notice the format I use. I write the equation. I solve it symbolically for the mass. I put the numbers in with the units. The meters per second squared cancel, leaving me units of kilograms. My impression is that the marks on physics usually like 2 decimal places. And these numbers are 4 significant figures, but the 9.80 is only 3 significant figures. So I'm actually not sure whether it'll accept the 54.1 or not. If not, put in the 54.8. I'm going to try 54.1 to see if it accepts it. If not, it means you should have put in the 54.08. Here we go. Took it. So this is a bit of a trick question. It's asking about the mass. Remember, the mass is the same on the moon and on the Earth. So Joe's weight on Earth is 600 newtons. His weight on the moon would be 100 newtons. But it's asking for Joe's mass on the moon. Well, his mass on the moon, is the same as his mass on the Earth. So we find the mass this way. And if I use 9.8, it comes out a little bit bigger than 60, but it says approximately. So I just use 10. I don't have to use my calculator. 600 newtons divided by 10 meters per second gives me approximately, notice these wiggly lines, that means approximately equal to 60 kilograms. We'll check that. Okay. The force of gravity is the weight of the object. Okay, go through all the statements and find the false ones. The mass of an object is the force of gravity. No, the mass, that's the weight of the object. The weight of an object on the moon will be the same. We know that's false. The mass of an object on the moon, yes, that's true. On Earth, more massive, yes, that's true. The mass and weight, no, that's false. This is the one that people always get wrong. The weight of an object is its mass multiplied by the force of gravity. The weight of an object is its mass multiplied by g. G is not the force of gravity. G, sometimes we call it gravity. It's acceleration due to gravity. So the weight of an object is not the mass multiplied by the force of gravity. That would be the mass times mg. So that's wrong. It's a little bit of a tricky question, but the MOPs force you to read carefully, and that's a good skill to have. Let's check. Okay, another one. When you do these questions, you don't have to write things out, but if this were a quiz question, this is the format you would use. So notice the weight is the force of gravity. The force of gravity is mg. There's the m with the units. Here's g with the units. Notice the units come out to be kilogram meters per second squared, which is a newton. So Joe's mass on Earth and on the Moon is going to be the same, but we know what G is on Earth, so we know his weight on the Earth will be 6 times greater. So 600 newtons. We just want an approximate answer, so I'm using 10. I get 60 kilograms. We do pay attention to units. Newton is kilogram meters per second squared, and so the meters per second squared cancel, and the units do come out to be kilogram. Checking. Okay, we saw one of these before. So this has no effect on the mass of the object, so we just use Fg equals mg. We solve for m. We put in the Fg. Notice I spread the units out so I can show the units cancellation. I end up with this number and more digits for the kilograms. I'm going to try this. It worked last time, just 3 digits. If it doesn't work, it means you should have entered the 2 decimal places. Sometimes the minds on physics don't follow the rules of significant figures. Let's see what we get with the 72.7. Okay, that worked. So 2 ways to think about mass. It's the amount of matter or stuff in an object. It's also inertia, or its resistance to change in velocity. So anyway, the amount of stuff would be the mass. Let's try that. Okay, speed does not affect the weight, it's only the mass, so we take the mass, multiply it by g. I didn't have room for the units, but it's kilogram meters per second squared. Whoops, I got those units wrong. The unit should be newtons, kilogram meters per second squared. And I'm going to test the minds on physics again, because by the correct rules of significant figures, this should be the answer, only 3 significant figures. If it doesn't accept this, it means that when you do it, you should add more digits. But I'm going to see, because I don't usually test the mops, I'm just going to try this answer. And although this is by significant figure rules, this is the correct answer. If it doesn't accept it, it means you need to put more digits in. I don't think it ever penalizes you for putting too many digits in. Let's see what happens here. Okay, it took it, but I think it would take the other ones as well. Okay, here we are in mission number 7. We're going to be talking about Newton's second law. The sum of the forces equals the mass times acceleration. Remember, you also have additional help button here. If you want more help on any of these questions, you can refer to that. So answer this and then come back. So by the equation, acceleration, and also just logically, more mass means less acceleration, more force means more acceleration. So this is an inverse relationship, this is a direct relationship, inverse and direct. Okay, read carefully and try to do this on your own. If you can't do it, I'll give you some hints. But try to do it completely on your own, and then if not, I'll give you some hints. Okay, 2 hints. One is use this equation to get the acceleration, and the other is well, actually they tell you it has a mass of 5 kilograms, but if they didn't tell you, you could tell from the gravitational force, right? It would be 50 divided by 9.8, or 50 divided by 10 gives you about 5 kilograms. So use this equation, and you can actually calculate 4 numbers, or see if you can do it without calculating. Since the mass is the same, the accelerations will rank the same as the net force. Okay, try that. Okay, so the net force on this one is 0, so the acceleration is 0, so that's definitely the smallest. And the net force here is 15, the net force here is 25, and the net force here is 20. Remember, we don't care whether it's negative or positive. So 15 is the next smallest. Now, if you divide 15 by 5, you're going to get 3, but you don't really need to do the math because these are all the same. So we can just rank by the net force. It's going to be direct. So I'm going to take the 15, that's A. Then the 20 is next. And then the 25 is last. You'll get the same answer if you actually do the calculations out. But you see, I was able to do it a little quicker without actually doing the calculations. So decreasing, decreasing acceleration. So decreasing the mass would increase the acceleration. Decreasing the net force would decrease the acceleration. Doubling the mass, increasing the mass, would decrease the acceleration. Tripling the net force would increase it. Making the mass smaller would increase it. So only B and C are correct. So once again, we're ranking accelerations and considering only magnitude, and we're going from smallest to largest. But now we have different gravitational forces, so we have different masses. So just use 10. If you divide this by 10, you get a mass of 5. Whoops. So this would have a mass of 4 kilograms. I'm just using 10. 3.5 kilograms, 2.5 kilograms. So I think in this case you should do all 4 calculations. So just do them. I'll do them and then we can compare our numbers. Okay, these are the numbers I got. Right, this is 40 divided by 10. I'm just using 10, so 4 divided into 20 gives me 5. 3.5 divided into 20 gives me that. 5 divided into 20 gives me 4, and 2.5 divided into 20 gives me 8. But after I started, I realized that all of the net forces are 20. So since all of the net forces are 20, the accelerations are going to rank inversely according to the mass, because the net force is 20. So this, if we want to go from smallest to largest, we go from the largest mass to the next largest, to the next largest, to the least large. So you could have actually done this, if you follow what I'm saying, you could have actually done it without doing the calculations, because the net force is the same for all of them. Anyway, that's the set of answers you should have gotten. Okay, this is what's called proportional reasoning. So acceleration is equal to this. If we decrease the force by a factor of 4.5, that means dividing by 4.5, then the acceleration would have to decrease by the same amount by proportion. So if I take the 12.5 meters per second squared and divide it by 4.5, I get this answer, and I rounded it to 2 decimal places. So let's check that. Okay, so we know increasing the mass is going to decrease the acceleration, and you can see it mathematically here because the 2.7 is in the denominator. And so we divide by 2.7 and we get this number, and I'm just going to try the 12.9. If that gets rejected, it means you should put in the 2 decimal places. Let's see what happens. Okay, it took it. So if the force increases by 2.5, then the acceleration has to increase by 2.5. So we get 12. Okay, so now you have to be a little more careful. So acceleration is equal to the force over the mass. If this increases by 3.3 and this increases by 2.5, then we have to do the same to the acceleration, and we get 7.92. Yay, that's a lot of calculations. Okay, we're in mission 8, more calculations. So it just says use 10, so since it says use 10, use 10. Just try to do this on your own first. Okay, this is a bit crowded, but let me show you the method. Now I'm following, what we do is we always break the sum of forces into the x and y components, and in this case, the only acceleration is going to be this way. These two forces are equal and opposite. There's no acceleration in this direction, and we're using g equal to 10. So this is the equation we want. We want the acceleration in the x direction. I dropped the x, so the acceleration is the net force divided by the mass. So the 20 is positive, the 12 is negative, and we get, by dividing the gravitational force by g equals 10, we get 4 kilograms for the mass. So we get a net force of a positive 8 divided by 4. We get 2 meters per second squared. Okay, so here we want to rank the masses. We get mass by rearranging the equation, then at force divided by the acceleration. We have all those numbers, so do the 4 calculations, and then we can rank the masses. Okay, those are the numbers I got. Hope I did it right. So those are the ranking I would get. So let's see if I got it. So this one's the same as the one we did 2 problems ago. We have the acceleration in the x direction. It's just going to be the net force divided by the mass. And so we have 50 newtons minus 25 newtons divided by 5 kilograms. I got that from the gravity force, dividing the 50 newtons by the 10, right, to get the mass. And that gives us 5 meters per second. And let's check that. Okay. Pretty much the same problem we just did, only this is 100 newtons, so this becomes 10. This would be 2.5. Since the force of gravity is 100, the mass will be 10. The net force is negative 20. That would be an acceleration of negative 2, not 14. The acceleration is leftward. The object would be slowing down because it's moving rightward, and the net force and acceleration is leftward. So those are the answers. You can pause and check. I'm going fast. So these are all pretty much the same. So I'm just going to show you. But notice the formatting. I start with the equation, put the numbers in the units, notice units cancellation, and I come up with the answer. Trick question, you need to read carefully. Net force, the velocity, constant velocity of 4 meters per second. It has to be E. Here are the answers I got. Notice the correct problem-solving format: equation, numbers with units, final calculated answer. Notice I got the 2 kilograms from 20 newtons divided by G. Okay, here's the table of contents.